Hello everyone, on behalf of Embarcadero Technologies, I'd like to welcome you to today's webinar with Karen Morton on understanding Oracle Optimizer statistics. Thank you so much for joining us today. My name is David Kong and I'm your GoToWebinar administrator for today's event. Joining me from Embarcadero today is Karen Morton. Over to you, Karen.
Great. Thanks a lot, David, and welcome everyone. As David mentioned, we'll be talking about understanding Oracle Optimizer statistics for the next 45 minutes to an hour. As he mentioned, my name is Karen Morton. I'm a senior technical consultant with Incatech. Here's my contact information where you can find me. You can also find me in print in few books that I've been fortunate enough to participate in authoring are shown there at the bottom. But without any further ado, why don't we get started and let's talk about statistics. What are statistics? I think starting at the very beginning is a very good place to start, and I would say that one thing about statistics that we can all understand, whether the term statistics kind of freaks you out or not, is the term odds. I mean, when you think about having the odds for something, it could be whether you're playing a game of solitaire or poker or some kind of card game, or heck, your odds on whether or not you're going to make it to work on time given the traffic each morning. But in the end, all statistics and all odds is about math. And one of the key pieces as a developer or DBA or anyone that is trying to understand the Oracle Optimizer and the execution plans that it derives for the SQL that you present it with requires a primary focus, I think, on understanding something about statistics and about the odds that are in place for how your query execution plan is going to be designed, and based on that design, will it perform to your expectations or not? So really it's just about math, and over the next few minutes I want to show you some simple math that is used by the optimizer in order to derive some of the operation decisions that it makes around execution plans. In order to do that, I want to start out with a very simple table. The table is called tributes. For those of you out there who are fans of the Hunger Games, this is a tribute to the tributes of the Hunger Games. So in this table we have just 6 columns: name, district, gender, age, qualification score, and weapon. So just some very basic information. And if we look at the statistics that are derived once this table is populated, what you'll see here along the top is that the table has 24 rows in it. And by the way, the statistics as collected here are 100% statistics. So with the table being as small as it is and so forth, it was very easy and very fast for these statistics to be collected. And they are, in air quotes, quote unquote, they are perfect. They are 100%. Or they were collected at 100% estimate, so each row in the table was actually examined to derive this information. So in the column statistics section, you see there the columns that are in the table. And one thing that I wanted to point out about the column statistics, are actually 2 things, is the second column there that's labeled NDV. That stands for number of distinct values. The number of distinct values is a very important statistic in that it is used as the primary number in the estimates made for how many rows the optimizer is going to think will be returned by various portions of your query. So when you see the NDV column, or the value in that column, for age, that's telling me that there are 6 distinct values of age present in the 24 rows. So that means there will be more than one person, let's say, that might be 12 years old, or more than one person that may be 15. Anyway, there's some duplicated ages in there, since there's only 6 distinct values. The density column represents a calculation for 1 divided by 6. What that is used for, it's basically telling us the percentage that any single value would occur in the table. So if I went out and said I want to know all the rows where the age is equal to 12, the density is saying, well, any one age, 1 over out of 6, that calculation amounts to about 16%, 0.1666667, and so on. So gender is actually quite easy. There's 2 distinct values for gender, so the density or the computed percentage for how many occurrences of each gender will be there is 1 divided by 2, or half, 50% of the data would be female and 50% would be male. There are also index statistics. We're not going to really get into those very much in this session, as we're going to be primarily focused on column statistics and how they work to help the optimizer make some of the base calculations. But obviously there are statistics on virtually every piece of an object that can be out there. There would be partition statistics and index statistics and so on. Now, I did want to show you just very quickly a couple of screenshots from the DB Optimizer product. I use this product quite often, and it has a section in the SQL analysis portion that will show you all of the objects that are used in a particular query, and it will show you the number of rows and the blocks and so on. So you see here just the sample of that. It would continue on to your right. You could scroll over to more data. I just wanted to show you quickly that that product actually does present a view of statistics that's kind of nice. It also has a second tab which shows you the column statistics, which also includes histogram data. And again, I really like this to get a one-stop shop of what are all my statistics for all of the objects used in a particular query, and this tool is a really neat thing for that. So with mine, I just did the simple little script to produce that output that I showed you for that one table, tributes, and based on that information, we're going to look at a few queries and see how things get calculated. The first concept I want you to get in your head is about cardinality. Really, all cardinality is, it's the estimated number of rows that a query is expected to return. So the formula for that, if you want to determine what that number of rows is, you simply take the total number of rows in the table and you multiply that by the selectivity for a given filter. Now that's predicate selectivity. It basically says take what is in your where clause and determine what percentage of the rows in that table will be returned based on that filter or condition in the where clause. So let's take a look at the first very simple example, and that's a query without a where clause. So if we ask for select from table and have an order by on in this case, what we're really asking for is we want the whole table. We aren't asking to filter any of it out. So our formula is basically going to be 24, which is the number of rows in the table, multiplied by 100%, or it would be 1 over 1 if we're talking about distinct values, so to speak. But we want 100% of the table. So our computed cardinality would be 24 rows. How many rows should this query return? 24. And we see if we actually execute the query, it did return 24 rows, and the estimate, highlighted there in the light yellow on the top line of the plan, also was 24. Now, for purposes of our discussion, I'm not really too concerned about the operation that was chosen. What I want to do here is just get you familiar with the calculations, and then we'll kind of add more to that, that basic foundation in a few minutes. So if you want everything, as long as your statistics are 100% accurate, the number of rows that are selected should match the number of rows that were estimated by the optimizer based on the statistics. And it was the case this time. But let's add a where clause. Let's put a filter in. And in this case, we want only the tributes who are female. So given our statistic said that there were 2 distinct values, female and male, that means that based on the way Oracle will assume the data to be uniformly distributed, that means that it will believe that half of the data is female and half of the data, or the rows of data, will be male. So the formula for computing that particular estimated number of rows would be total number of rows in the table, 24 times 1/2, or 50% of the data, equals 12. And as you can see, when we execute it, we get 12 for the estimate, we get 12 for the actual rows returned. Now, it just so happened that our data really and truly did support that even distribution. There is one female tribute and one male tribute for each of the districts. So it was an even distribution. So again, our statistics were perfectly accurate, and therefore our estimate was perfectly accurate. The next one, what if we add a second condition to it? Well, originally when we asked for just the gender as female, we knew we were asking for basically half of the population of the table. Well, what if we want to get just the tribute or the row from our table where the district is 12, so there are 12 districts in the table, and where the gender is female? The computation for that would be taking both of the selectivity values for each predicate and multiplying that by our total rows in the table. So there's 12 districts, so we would want 1 out of the 12 districts, and we would want 1 out of the 2 genders. The math ends up being equal to 1. And when we execute, we actually do see that we get 1 row returned, and 1 row is the estimated answer that the optimizer came up with. Now, I did want you to notice that in this particular plan, if you look at row 2, or ID, marked by ID number 2, the index scan that was used has an estimate of returning 2 rows. And if you look at the predicate information down at the bottom of the screen, it says at step 2, it is accessing the information in the index by district, and it's looking for district 12. So you'll notice that it says there's 2 rows at that point, and we know that that would be true. For each district, there are 12 of them in the table. There's a male and a female. So in this case, it would get our 1 out of 12, 1 out of 12 total districts, and it would return that. So there's only 2 people in each district. Out of the 24, there'll only be 2. And then it will further filter it by gender to return a final answer of 1. So you can see how it actually got the estimates right on each step of the plan. What if we needed something that wasn't an equality? So instead of having where gender equals female or district equals 12 or what have you, we actually have a range predicate. So in this case, we're asking for where the age is greater than 15. Well, if you recall, our statistics told us there was ages ranging from 12 to 17 in the table. So our computation in this case is just a little more complex. You'll see on our at the bottom part of the screen, you'll see that the first part of the calculation is you need to figure out kind of what the top number is in your percentage calculation. So you start with the high value and you subtract from it whatever your predicate is asking for. So in this case, 15. So you're basically saying if you have 17 as your highest value and you want anything greater than 15, you want whoever is aged 16 and 17. So there's only 2 of those. So that gives you the top portion of the calculation here. The lower half of that calculation is also takes the total, or the highest value, which is 17, but now it has to say, well, how many values are in the range? So it subtracts from the high value the low value, giving us 5. Now, when you do the math and you say 24 times 2/5, your answer is 9.6. Well, we deal in whole numbers with the optimizer, so that's going to get rounded up, and if you take a look, the optimizer says the estimate is for 10 rows. Now, if you'll notice, we actually got back 12 rows, so it wasn't perfect in this case. We didn't exactly match on our estimate to our actual, but it was very close, okay? So, again, what you have to remember is that the optimizer is going to assume uniform distribution. That means equal distribution of all values as its initial way of going about doing calculations. So when it isn't exactly equal, that's when your estimates and your actuals start to diverge. So what we're seeing here is our first divergence from being 100% on the money. So, but again, we're really close, great estimate, and let's see what happens if we do something else. What if we use a bind variable? Now, with bind variables, you have several different things that come into the mix. If we were to ask for a specific weapon like an axe or something like that, and we were to hard code that literal in here, the optimizer can actually be very specific about the computations that it uses to figure out what plan choices to make and how to do the estimates and so forth. But when you use a bind variable, the optimizer is going to do something as its first pass during the hard parse of the statement, which is it's going to peek at that bind variable. It's going to look and see what value is inside or captured and used by the bind, and it will use that value to make its estimates with. So let's say that we chose bow and arrow was the weapon. The optimizer will use the information stored in the statistics saying there are 11 different types of possible weapons. You're asking for one of those, and our computed cardinality would be 2.18. So at this point, based on rounding, the optimizer should say that we're going to get 2 rows back where the weapon is equal to bow and arrow. And as you see here, the estimate was 2. The actual was only 1. So once again, we're not exactly perfect, but we are close enough in this case to say that we've got a really nice estimate for that. Now, I will mention quickly about bind peaking. Bind peaking is a problem when, or can be a problem when you have skew in your data. And we're going to talk about data skew in a few slides from now. But the one thing I want you to keep in mind is that through the later versions of Oracle, issues regarding bind peaking have been dealt with by the optimizer in better and better ways. One of the things that used to happen was that when you used a bind variable and the optimizer peeked at that bind and saw bow and arrow the first time that it parsed that statement, it would continue to use the same execution plan whether it should or not, because it would use it that very first time, come up with the plan, and then if the statement was ran over and over and over again, it never looked back at the bind variable to see if it changed and if that change would require a difference in the plan. With the advent of adaptive cursor sharing, things like cardinality feedback, and so on, the optimizer is getting much better at being able to adjust when plan differences should occur based on different bind values. Now, it's not 100% perfect still, but it is getting better. So I just wanted to mention that before we move on. So in the end, the truth about how statistics, particularly the base calculations, work is that it's not really any kind of trick. It's just math. And it's relatively simple math. Now, obviously, all of the examples I showed you were using single table, but the more tables that you put into the mix, the basic rules still say the same. For each table that's involved, you would look at the predicates, the filters in your where clause and the columns that are being used by those, and you could do the computations to start doing the math on your own to figure out how many rows should come back and so forth. Based on those decisions, the optimizer is going to choose all of the particular options in the plan that it thinks will give you the best performance. But you got to be asking the question, though, what happens if your statistics aren't perfect? Okay? And in some cases, the truth is, even if they are perfect, you don't always get what I'll say is perfect results, because statistics, if they don't reasonably describe your data, okay, so if you have old statistics, stale statistics, missing statistics, if they don't describe your data accurately, then that's going to lead to poor cardinality estimates. Imagine with some of our examples that I just showed you, what if the statistics had been incorrect? What if it said there were 1,000 districts instead of 12? It would come back with very different estimates than were made when it thought there were only 12. Okay, so if the statistics that are in place for the optimizer to use in its calculations are off, that's going to give you poor cardinality or row estimates. That can then lead to poor access path selections. So it may have a problem with being able to figure out which index to use or whether or not to use a full scan or a particular index scan. If it has problems with figuring out how to go get the data, then that can lead to problems with how do I join the data. If the method that it uses, such as a nested loop or a hash join or so forth, is not done so well because of bad estimates, that can lead to poor join order. How does the optimizer know if the estimates are wrong? What's the best order in which to join something? Should it join table A to B or B to A? With bad estimates, that becomes a problem. And ultimately, all of these things can lead to poor SQL execution times, and that's when the problems arise. When we get plans that are inaccurate for whatever reason, but if it's due to statistics, the bottom line can simply be that we get bad SQL execution times, not due to the fault of how the SQL was formulated, but simply with based on the information that the optimizer has is inaccurate, and it leads it to make poor choices. Okay, so sometimes we can have a large hand, or the way statistics are collected in our database can have a large hand in why SQL doesn't perform optimally. So statistics, they really do matter. Okay, that's the bottom line for the optimizer, is statistics are at the heart of it. So one of the things that I also think you need to remember is that the solution that is used by default, or all of the default parameters for collecting statistics, are intended to provide a solution and collect stats that are good enough to meet most of the needs of most of the people most of the time. Okay, there's really no way that Oracle can come out with one mechanism that is going to be perfect for every person, every company that purchases their software and runs their database. Because each different application may have nuances. It has specifics about how the data was designed, the data model, the content, and so forth. So when it's good enough to meet most of the needs most of the time, that's probably going to imply that you're going to need to do something special on occasion. And I love this quote because I think it's very true. It's very true with statistics collections. Say you were standing with 1 foot in the oven and 1 foot in an ice bucket. According to the percentage people, you would be perfectly comfortable. You know, well, we know that's really not true. You're going to have 1 foot that's too hot and 1 that's too cold. Same works with statistics. If some of the statistics are off by, particularly by orders of magnitude, you're definitely not going to be comfortable, as your SQL execution plans are going to suffer for it. Now, as I mentioned earlier, I wanted to talk just a little bit about data skew and how that affects the optimizer's ability to compute good plans for you. Now, as I mentioned, the optimizer does assume uniform distribution of column values. Now, what that again means is that if you were to have, say, a column color and the table had 100 rows in it, by default, the optimizer is going to assume that if there are 4 colors present, each color would be uniformly distributed among the rows. So there would be 25 yellows, 25 blues, 25 greens, 25 reds. That is the assumption that is being made. Now, what if your reality looks more like this? What if you have 85 rows have a color of red, and only 5 of each have yellow, blue, and green? Okay, that is a very, very different picture than what Oracle is going to assume by default. So what do you have to do? You have to let Oracle know that that skew is present by using a histogram. Now, the example I wanted to show you involves creating a table, got about 1.6 million rows in it, and I have a column object type. Now, if I collect statistics on this particular table, 100% statistics, and I am going to not collect any histograms. But if you look at the bottom of the page here, you'll notice that for the various object types that are present in the table, there are 2, Java class and synonym, which represent the majority of the rows. So 40% of the rows will have an object type of synonym, 32% of the rows will have an object type of Java class, and all the other object types will only account for a very small percentage of the rows. So what would that tell me I might desire to happen if I query this table? Well, let's take a look. If I query from the table and I look for an object type of procedure, procedure is an infrequently occurring object type value. So if you'll notice here that when the optimizer computes the estimated number of rows, it is using the concept of uniform distribution, and it thinks that procedure is going to be one out of, let's say, 12 or 13 different object types. Okay? And based on that percentage, it estimates to return about 44,000 rows. But in reality, it only returned 2,700 rows. Now my response time was fine. It was 0.06 seconds, so it was sub-second response time. Used an index, nobody's going to complain about that. But what happens if I then query for the same table with an object type of synonym? Okay? Notice that the estimated number of rows is exactly the same, and my actual number of rows is 640,000. It's definitely orders of magnitude off in this case, but the optimizer has still chosen to use an index range scan, and the response time appears to have suffered quite significantly, taking over 14 seconds to complete. So what could happen different if the optimizer knew about the actual values instead of just going on this uniform estimate that it had used originally? Well, if I compute or gather the statistics again, I can tell it to go out and gather histograms for me using the size auto option. This is the method opt parameter in the statistics collection. And with size auto, the collector will actually go out and look to see if the predicate, in this case object type, has been used in the past, and if it has, it can compute a histogram to be able to tell tell the optimizer that this column is skewed, and it can define by object type how many rows are present using a frequency histogram. So in this case, that's what happened. A histogram was developed. The estimate rows now for procedures matches identically my actual rows, and my response time is basically the same. Now when I query for synonym, notice that my estimate and actual are also the same. But the really neat thing is that now I no longer get an index range scan, I get a full scan. The optimizer realized that if I'm going to get that large a percentage of the data, it made sense to just do a full scan rather than an index access, and you can see that for this particular table, the response time was reduced from over 14 seconds to just over 3 seconds. So it's a significant benefit, all because the optimizer was able to distinguish that this column had skew in it. Okay? Without the histogram, this isn't going to happen. With it, it can. Now, another thing that I wanted to point out to you is something called dynamic sampling. Dynamic sampling can be implemented through an instance level parameter or a hint that can go into your SQL. Let's start out by creating a table to use for this particular test. Now what I want you to notice about this table in the creation is on lines 2 and 3 of the create statement, I'm creating 2 columns, C1 and C2. These columns are created identically. What that means is that they will both contain exactly the same information. It would be the same thing as if I had a department table and I had department number and department num, two different columns, but they had the same thing in them. Okay? So with that in place, I'm going to gather the statistics. No histograms or anything at this point, but I'm gathering statistics. And you'll see that in the statistics that the column has 100 distinct values going from 0 to 99. And both column 1 and column 2 look to be identical. And we know, based on how we put the data into the table, that they are. So what happens if I go out and I want to query from this table? Well, if I'm querying and I ask for where C1 equals any value, I'm going to get 1% of the data. How do I know I'll get 1%? Well, if I look at my density value, again, which is the computed answer to 1 over the number of distinct values. So for any single value, I would get 1% of the data. So what I would expect is if I have a where clause where C1 equals 10, my row estimate is going to be 100 rows. And that is, again, perfectly correct based on how I loaded the data and so forth. I know that's correct, right? Well, what happens, though, when I add a second predicate? What happens if I add C2 equals 10? Well, we know that the same rows that have C1 equals 10 will also have C2 equal 10. We know that because that's how we loaded our data. But notice what happens from the optimizer's perspective when it computes that selectivity. It multiplies the two selectivities together so that what it will get, instead of 100 row estimate, it comes up with a 1 row estimate. And that's wrong. The answer truly is it's still 100. But the optimizer has no way to know that because it treats these two columns as if they were independent from one another. In order to let the optimizer know that these columns are related so that it can adjust the cardinality estimate based on that information, one way to go about doing that is by using a dynamic sampling hint. At level 4, dynamic sampling allows the optimizer to understand the relationship between these two columns. It can see, based on the statistics and so forth, it can determine that these columns pretty much contain the same stuff, and therefore they have a relationship. So it will produce the accurate estimate for rows, 100, even with the two-column predicate. Okay, and that is if I use this particular hint, or if I have the dynamic sampling, optimizer dynamic sampling parameter set to 4 at the database or instance level. Okay. Now, what if you can't go around sticking dynamic sampling hints in everything, and you don't want to set your instance parameter to do that? But you have cases where you have these kind of relationships between columns. That's where extended stats comes in. With extended stats, you can simply use the create extended stats procedure in the DBMS stats package and tell it, for my particular table, these are the two columns that are related, and it will produce, in effect, a pseudo column. This column is the combination of C1 and C2 in this case, and when statistics are then gathered, that column, that combination column of C1 and C2, will have its own statistics computed for it. Excuse me. With those statistics available, I don't need a hint any longer, don't need for dynamic sampling to be invoked. Instead, the extended statistics give the optimizer the ability to produce a correct row estimate using that new statistic. This is a fantastic tool to use when you have data that is related inside of a table. So column values are related to one another, and you want to express that to the optimizer. Extended stats are a fantastic option for that. Now, the last part of what I wanted to talk to you about today has to do with how you write SQL and the subject of query transformation. Now, once you've kind of gotten a grip on how the statistics are going to work and how it influences the decisions the optimizer makes, there are also things that you can do about how you write your SQL that can help the optimizer. The bottom line is that the optimizer is always going to want to try to come up with the best statistical formulation that it can. And in order to do that, one of the things that occurs, it's actually a very early step in the optimization process, is called query transformation. What query transformation does is before any of the cost estimates are made or anything like that is done, the optimizer is actually going to make an attempt to rewrite your SQL. The goal of that is to be able to make more choices, to give it more statistically valid options for plan generation than it may have with the current syntax. Now, what it will do is it'll create a fairly equivalent statement, which as far as the semantics of the statement are the same, so that you get the same answer. In other words, it can't write the SQL so that it changes the answer that would be produced. As long as it gets the same answer, it can rewrite it however it wants to. It can do that by removing extra conditions. It can add inferred conditions, all of that. What you want to do here is think algebra, okay? So back in high school or middle school when you learned some of the basics of algebra and transitivity and things like that, all of that starts coming into play with how the optimizer does query transformation. But you may be asking the question, this is usually what I get. It is, so, well, if the optimizer is going to transform or rewrite my SQL for me, why do I care? You know, why should I write it any differently than I'm going to? Because the optimizer is going to do it for me, right? Well, not necessarily. One of the things that I like to suggest is that you know your stuff best, or at least you should. You know how your data works together. You know your data model. You understand the nuances of it. Those are the kinds of things that, remember, statistics collection and how the optimizer does things is based on general, broad concepts that should work for most of the people most of the time. If you know specifics, you're the one that's going to be best equipped to provide or write SQL to take advantage of that knowledge. It gives you the ability, when you write your SQL in a way that expresses that knowledge, gives you the ability to filter early. It means you can take large data sets and get them filtered down or reduce the number of rows being manipulated sooner in the process rather than later. That's always going to help with performance. Rather than carrying a whole bunch of stuff around through a plan for multiple steps, the sooner you can get rid of it, the better. So if you can affect that, great. The other reason why it's really good for you to rewrite or refactor your own code is that it helps you define your expectations. What are you thinking should happen when this statement executes? The way you write the statement is reflective of what you expect to occur, or at least it can be. And it gives you the ability to keep it as simple as possible. Okay, so you want to make it understandable to not only you, but to the optimizer, okay, as well. And the bottom line is that the optimizer may not always be able to rewrite or transform the query to make it be the most statistically accurate choice, okay? So you have the control when you use your knowledge of the optimizer and statistics to write SQL in certain ways. There's lots of very common transformations. These are just a few that I wanted to mention or show you an example of. Simple view merging. In this case, I have an inline view. The parens to most people mean execute me first. That's not the case with how Oracle works. Without a hint, that statement will actually be transformed to what you see at the bottom of the screen. It takes that inline view and merges it in with the other tables involved in this query to become a four-table join. Now, the idea here is that if the optimizer has all of the tables available to it for producing the join order and join methods and so forth, it will come up with a statistically better alternative. So not that you have to rewrite your queries to look like the bottom part, but you need to know that a query that looks like the top is probably going to get rewritten to the bottom format. If you take the opportunity to do that yourself, again, it can help you define your expectations. If your expectations were that it needed to execute what you see in parentheses first, then you would have to know, you would need a hint or some way to make the optimizer do that independently. Complex view merging, in this case it's a very simple example. The reason why it's complex is because it has a group by in it. Anything that has an aggregate type function in it, Oracle will consider that more of a complex nature. So what you see here is that if you have a query that uses a view as one of the objects, the optimizer basically is going to transform that to take the source of the view and the tables involved in the select statement and create a new SQL statement, which is basically the combination of the view source and the query. Now, the reason why this is done is it simplifies it. So it doesn't, again, treat the view as a separate entity, which can allow it to do filtering earlier and so forth. So once again, it's just something for you to keep in mind. Not saying that you should take all your views and get rid of them and write just the basic queries. Views are used for reusability and so forth, and there are good reasons for them. But make sure that when the execution plans are derived from them, that your results are coming back as you expect. Okay. Another good transformation for you to keep in mind for how you write things is the one shown here. Again, we have an inline view. Now, in this case, it's doing a group by with a count. And then on the outer query, it is saying, well, after you've gone through and grouped up all of the data and got my counts, I only want to return rows from that list where the count is greater than 2. Notice how that gets transformed into a group by with a halving. Okay. Now, once again, the purpose of this is to allow the filtering to occur earlier. It can do some things with how it manipulates the data so that the number of rows that have to be moved throughout the plan can be filtered sooner rather than later. Okay. So it's another option for rewriting. With predicate move around, what this does is it again allows you or the optimizer in this case to say, I want to take a predicate from the outside, let's say where the max is greater than 25. It doesn't want to wait until the very last part of the plan to do that, but rather it moves it into that inner select. See that first select? If you transform it to pull that up sooner, that means that that portion of the query plan will deal with fewer rows. The other thing that occurs in this particular example is that when you have a predicate that can be duplicated, in this case we're actually joining the two tables on the player ID. So if my first subquery had a condition where player ID equals the value shown there, I can actually include that in both of the queries in order to, once again, filter as soon as possible. Now, that particular optimization is one that the optimizer is going to make very easily for you, and it may look redundant to you to put the same thing in twice. But, again, something to keep in mind. These kind of things are added to help make it more efficient and produce earlier filtering. Excuse me. The next one is joint factorization. I like this example because what it shows is where you have a union all type query or a union query where I am querying from a base table called schools. In the top portion of the query, it's asking for Georgia state schools, and in the bottom, a Florida state schools. But you'll also notice it's joining to a second table called schools players. Now, that schools players table is going to provide a player ID. Now we're going to need that for the final answer, but we don't really need to touch that table twice. Why? Well, because all we really want is we want rows for schools that are in Georgia and Florida. Now, I could rewrite this even more different, but it's to kind of prove the point out here that if I join or I union the schools table for Georgia and Florida to start with, I can then join that union to the schools players table and only have to touch that table one time instead of two. Reducing the number of accesses to a table is a good thing. Okay, doing something once instead of twice or once instead of three times or what have you is going to provide better responsiveness, less resource use overall. Okay, so these are just some simple transformations that you can mimic or learn from in the way that you write your code. And most of the time the optimizer should be able to do these kinds of things for you, but not always. So keep the thought in your mind that you can affect the way things are computed in the plan. Estimates are computed, how joins are made, by the way you write your code. Okay? So understanding how these transformations occur will help you write better SQL and understand the way the execution plans work. Now, in conclusion, with this, you need to keep in mind that statistics have got to be representative of your actual data. Okay? Now, that may involve extended statistics. It may involve histograms on certain tables and so forth. Those kind of things have to be in place in order for the execution plans to be able to be derived optimally. Okay? Understanding how statistics work is a key to all of it. Okay? It's not just something that we don't need to think of as developers. It's not just a DBA job to figure out how to get it computed. Understanding how statistics works will make you a better developer. It'll make you more able to respond to performance problems when they occur because you understand why things are happening. Writing SQL to utilize all this knowledge will help the optimizer, and if you help the optimizer, it can certainly help you. The more you know, the more likely your strategy is going to be more effective, and the way you write SQL will help by supporting the derivation of more optimally performing execution plans. It's cool stuff. So take some time, get to know the optimizer, get to understand how statistics work, and it'll build a really great foundation for making sure that you get good performing SQL and help maintain it over the long haul. In the end, just keep calm and may the odds be ever in your favor. Thank you very much, everyone. I think we've got a few minutes now for a quick demo for you of the Embarcadero DB Optimizer tool. And then after that, we'll, if we have a little bit extra time, we'll take a few questions. And if not, I'll make sure to get the transcript of all the questions and answer them on my blog as a follow-up. So, Scott, I'll turn it over to you. And again, everyone, thank you very much.
Thanks a lot. Thanks a lot, Karen. And it's a tall order to follow somebody who can intertwine Oracle statistics with the Hunger Games movie and book. So I'm going to try my best. So great job, Karen. And really quick, I know Karen alluded to it earlier in her presentation, DB Optimizer from Embarcadero. So while Karen is looking at the questions, and thanks everyone for those questions. I was monitoring those, and they were coming in fast and furious, so that is great. I just wanted to really give you a quick overview of what we do within DB Optimizer. So here we do really four things. It's a SQL editor. It's a SQL profiling tool, which you're seeing a profiling session here. We can tune queries, and showing some of those same statistics that Karen pointed out. And lastly, we can load. We can actually apply load against the database. Here we're looking at a stored off profiling session, and we're showing things graphically, right? So we can drill in, drag and drop, really narrow down and see exactly what's happening within a certain time window. Then from there, drill in and take a look at the exact SQL being run, and then look to see what else we'd like to do. We can look at the SQL details, the events. Now this was all executed against a Oracle machine in our lab in Toronto. I don't have access to that, but I just wanted to point out though that because it is a stored file, I do have the ability to see all the details. So even if I don't have access to the data source, I can still look in there and see exactly what's going on. That's a profiling session, and I'll show you how we can certainly do that. We can right-click on the data source and then profile as, and then select data source, and you're off and running. The thing that I'd like to point out, though, is the tuning section of it. So as Karen mentioned, we have the ability to tune SQL. So here is just a very vanilla SQL statement that I'm working on tuning here. I purposely left out a join to the office location table. So again, you'll see that even though I have it as an in, it's missing from the other join, and I'll point out how that looks there. So we can look at the different iterations, the different permutations that we were. DB Optimizer generated 40 cases for us. So it found the missing join criterion for us. It tried to find some into exist to rewrite those, as well as a between, trying to figure out how it can rewrite that to perform a little bit better. If we look at the missing the join criterion, I can look to see here by drilling in, and we can see that DB Optimizer did indeed find that where clause and brought that join back here. And you can see that that turns out to be the fastest iteration. So from here then, I can hop over to the analysis section. So I'm looking at my initial table. I'm sorry, the initial query, and I can look over here to the right as our visual SQL tuning diagram. So it's different than an explain plan. We deconstruct the query and bring it in and reconstructing it, and looking at some of the important elements here. We're looking at the relationships, the actual counts, as well as the ratios. Right? If we want to see where it's accessed in the query itself or the indexes below, we can simply select the object. If it's a view, we can double-click the view and actually see what elements are used to construct the view. Here in this visual SQL tuning diagram, we can see that we pretty much, it appears as though we have two distinct diagrams, and that's because there is a missing join. If I drop this down and select that transformation join, you can see now that it's all related. So this is really what we're after, and in this situation, DB Optimizer was able to find that. If we step down here, look at some of the stats that Karen mentioned in her and the screenshot she showed, we can look here to see the information about the statistics from the table level, and scrolling to the right, looking at the empty blocks, the sample size, and attributes, and other information. We can look at column stats and histograms if needed. If there's any stored outlines, we can certainly reference those as well. And going back to the index analysis, I'm going to jump over to another tuning session that I had to show you the full features of the index analysis. So here we have an orange one. Orange is letting us know that there's a potential additional index that we could add that could improve the performance of this query. Green, simply letting us know that this query is used by, this index is used by this query. If it's in blue and the index is defined on a column present in the predicate, so it could be used by the optimizer when you run the statement. We're not 100% sure, but it could be. And if it's in gray, it's not used at all. So again, that's the index analysis section of the visual SQL tuning area. So if I right-click and select Profile as Data Source, I'm going to let that start up running. And I want to point out here, and here is our SQL loading utility. So if you'd like to add load, we can select this statement here. Very simple statement. I'm going to, number of parallel sessions are 15. Number of executions, I'm going to drop this down to 50. And we can have a sleep condition between the executions. And I'm going to uncheck that. I want it to run as soon as one session's finished. I want it to start back up again. So if I press execute there, you'll see that we'll start applying load against the database. And so let's hop over and let's look to see. Probably not a lot of action going on here. So we're seeing a little bit of activity, not much. Let me go back to my SQL load utility here. And we'll select a fixed delay, and then we'll execute. And my machine is dragging along. So anyway, the point is that we're able to execute the profiling session as well as apply load to the data source. I see my problem here. My data source is not connected. Then we can go back. But on having said that, and I'll turn it back over to Karen now so we can get those answers that she might have for any of those questions before we run out of time for the hour. So Karen, I'm going to send it back over to you, and I'll make you the presenter to finish up.
All right, great. Thanks a lot, Scott. I can attest to the usefulness. I'm going to get all the way to the end here of the DB Optimizer tool. I use it. Oh my! I use it quite frequently, and can highly recommend you take a look at that. It's got some great stuff. Just to get a few of the questions, there were several here that I think we can answer quite quickly. So the first was, are the terms selectivity and density used interchangeably? I'll kind of caveat that just a little bit, but say yeah, basically. Density is the computed value for the 1 divided by the number of distinct values. Selectivity is basically the percentage. So yeah, they're pretty much the same, but selectivity calculations are the composites. So if you had 3 different filters in your where clause, the overall selectivity would be all 3 of those put together. Density is for a single column. So that's really the nuance there. But in general, they're pretty much the same. It refers to the percentage of data that you're going to access. Next question was about the method opt parameter. And it asks, what value would you recommend for the method opt parameter when you gather schema stats, and should your recommendation be different for, say, Oracle 11.2 versus 9.2? I will tell you that by the time you get to 11.2, the default value for method opt, which is for all column size auto, is very, very good. Okay, and I can recommend its use in most cases. Now, what I would say though, if you're using an older version of Oracle, if you're back in Oracle 9, and even in some in 10, the size auto algorithm wasn't as robust as it is starting in version 11. So there were some cases where it over collected or didn't collect something that it should. So if you're running 11, I would say that you will have much better luck using the default for all column size auto, but you may need to, particularly with the earlier versions, may need to do a computation for maybe size 1 as a general rule, and then collect histograms only where you know you need them. So it requires some knowledge on your part to know where histograms are best served. Let's see, the next question was which version did extended stats come out in? That was in 11. So starting in Oracle version 11, extended stats became available. Dynamic sampling has been around for a while though. So the idea of how extended stats works is similar to what using dynamic sampling level 4 does. And there was another question about why the dynamic sampling hint caused the 100-row estimates for the 2-column predicate. And it was because the dynamic sampling level 4, like extended statistics, sees the relationship between the 2 columns. And that is the key. Normally, the optimizer will consider all of the columns independent of one another. And when you have dynamic sampling level 4 or extended statistics, the optimizer can understand the relationships or dependencies between columns and thus change the statistical calculation to be more accurate, okay, as it understands those particular relationships. Another question is there a way to see the transformed statement? You know what, I would give anything if it would just spit it out somewhere, but it really doesn't. The closest you get to it is in an optimizer trace. That is a 10053 trace that you can collect. It produces basically a a list of everything the optimizer considers as it develops the plan. And in that list, it shows you all of the different optimizations and transformations that it considers and lists them. However, it does not show the transformed code. It will simply let you know that it's considering predicate move around, it's considering join factorization, what have you, and it will give a note or a message that indicates whether or not it used that. So it won't give you the text, but it'll give you notes in that 10053 trace that tells you that it was used. So in that aspect, you can kind of sort of see what it's doing, but you don't get the exact text. Okay. Let's see if I see anything else in here. There was another question here. It says the assumption is that the last row in the stats, I guess in the plan, is showing the optimizer's estimated row the SQL return. Yeah, at the very, very top, so line 0 or line 1 in a plan, that's the kind of the final answer as to what the estimate is. At each step along the way, it is the estimate for that particular step. So, will there be a Word doc of the presentation? Yeah, actually there will be a PDF of it that will be posted both at from Embarcadero. They'll send you an email about that, and will be posted on my web blog as well later this afternoon or early tomorrow. And then I think the last question here is, what would be the difference between letting the out-of-the-box gather stats run versus just creating the gather stats on specific schemas that is used by the application? Well, out of the box, what Oracle does is it actually has a scheduled job that looks for stale statistics. And for many people, that can work just fine. The way stale stats work is that when there is at least a 10% change in the data that has to do with inserts, updates, deletes, if at least the data is changed by 10% based on those counts, statistics will be collected during the next statistics maintenance window. And it uses all the defaults unless you change any of that, all the default settings. However, different people may find that for their applications, one, they don't want statistics kicking off at unknown times. It could happen on Tuesday night, or it could happen during the middle of some large batch run, or you could have it kicking off on some other occasion where the next day plans start to change and you're not really sure why. So one of the biggest reasons why I see people not using the out-of-the-box stuff is because it feels like they don't have enough control over it. But like I said earlier, things are getting better in the later versions, Oracle 11, and from what is coming down the pike in version 12, I think we've got a lot to look forward to, and how much more robust what Oracle does provide out of the box works. But I think you always have to err to the side of caution and make sure that you are collecting stats that support your application and its needs with your own specific considerations. So with that, I think we'll call it for now. But if there's any other additional questions that you put out there, I will make sure to get the transcript of those. We'll answer those and put them on my blog. And once again, I really thank Embarcadero for the opportunity and for you guys for attending. And we sure appreciate it. Back over to you guys, David.
Thank you, Karen. And for information on Karen's blog, I posted that in the chat window, as well as the DB Power Studio Facebook page. So with that, we've come to the end of our presentation. Your feedback is very important to us. Please see the chat panel to take our 1-minute survey to give us your feedback. And we always want to improve and provide webinar topics that are the most relevant to you. And it's because of your previous feedback that we are able to now work with Karen to present today's webinar topic. Also, if you're interested in other Embarcadero events going on, please visit our events page on the Embarcadero website or connect with us on Facebook and Twitter. If you've missed any portion of this presentation, the recorded webinar will be made available within the next few days on the events page of the Embarcadero website. We'll also be sending out a follow-up email with the recording as well as the slides within a week. And again, on behalf of Embarcadero Technologies, I thank you for attending today's event, and have a great day. Thank you.